Assalamu alaikum guys. At present I have 12 section A वाले भी time पे नहीं आते. Section A, Section B regularly late in the class. दोबारा रिफिल कर दे लगा Shear, what's the reason why the students are late? I think Shear is also not in the class.
No sir, I am present.
Okay. ठीक है, तुम्हारा नाम मोहम्मद जवाद है. मैं जवाद देख रहा था. Okay, wait one more minute because we have to do 2-3 derivations today. ठीक है जी, and I want those derivations to be finished today so that we are just left with one topic, that is the theories of failure, which we can cover in the last week, which we will cover inshallah in the last week. And that will require 2 hours. So if we see the last week, in the last week you will have 3 hours of theory. So with one section, 2 hours lecture, let's say I will take, and 1 hour lecture Dr. Numan will take. So we need to arrange 1 hour additional lecture. So let's see who will that class be. Abdullah Zahid, Abdul Rafi, Amir Sultan, Anisa, Asad Rahman, Danish. When you guys will come to the campus, we will have one class in which we will have what you say interaction, and I will address your questions. But before that you will have the mid exam, because when you will come immediately you will have the mid exam, and then you have 3 weeks of psychomotor, and then you will have interim exam. I have already shared the class notes with the CR 2 week ago, in the last week. So stress transformation, that will be your mid-semester exam. Strain transformation, that will be your end semester exam. And if you will have any query, generally students have issues in solving the numerical. So what you can do, you can solve it on your like paper, take the photo and highlight where the problem is so that I can help you out. Like where you need help, you just indicate it so that I can help you out there. जुबानी कलामी कोई हेल्प नहीं हो सकती, लिख के होती है. यदि आपने यहाँ तक न्यूमेरिकल सॉल्व किया, you find it difficulty here, so then I can let you know how to solve it. Are you guys ready now? I think we should start. Okay, ji. Let me start the recording, guys. Today you need to write down the derivation, so you need copy pencil. Okay, ji. So let's start the lecture. Okay, ji, Bismillah Rahman Rahim. Over today's lecture is material property relationships. We are following chapter 10, strain transformation from R.C. Hibbeler 8th edition, and today we are going to study material property relationship. So in this section, we will present some important relationships involving material properties. In the material property, basically, you can say Poisson's ratio and modulus of elasticity. ठीक है जी? So material properties basically include Poisson's ratio and modulus of elasticity. In this section, we will present some important relationships involving a material's properties that are used when the material is subjected to multi-axial stresses and the strain. Multi-axial stress and strain means that in case of triaxial stress state, you have sigma x, sigma y, and sigma z. Three normal stresses acting on the element. And in case of the plane state of the stress, you have two stresses, sigma x and sigma y, acting over the element. So to do so, we will assume that the material is homogeneous and isotropic. Basically, first let's discuss what is isotropic, because it's relatively a simpler term than homogeneous. Isotropic basically means that your material has same property in different directions. Steel is an isotropic material, so it's a big advantage of the steel that you just need to measure the properties in one direction and the same properties will be there in the other direction. Like modulus of elasticity in tension and compression is same. So that's why you have seen that you are just performing tension test and you are not performing the compression test on steel bars. Whereas there are some other materials like fiber reinforced polymer composites in which they are non-isotropic material, or you can say orthotropic material, having different properties in different direction. In that case, you need to do tension test and compression test because the material properties are different in different direction. So steel is a big advantage. It's an isotropic material, meaning it has same directions. It has same properties in different directions. Then material is homogeneous. Homogeneous means that basically you can say matrix and the fiber or the composite as a whole. It has almost similar properties, so that you can say linear elastic behavior can be assumed. Okay? If you have heterogeneous material, in heterogeneous material means that the material different materials have different properties, so that result in heterogeneous non-linear type of behavior. But in homogeneous, where the material have almost similar properties, that will result in linear elastic behavior. Okay? So let's start with generalized Hooke's law. Generalized Hooke's law. Now let's have a look at the figure first. So this is element. This solid shape is element, and it is subjected to multi-axial stresses. You can see sigma x, sigma y, and sigma z, and they are all positive stresses which result in tensile stresses, which are positive stresses, result in elongation of the element. And you can see this dotted line is the elongated shape of the element. This is the elongated shape of the element. Now this is basically, you can see sigma x will result in elongation along the x-axis. Sigma y will result in the elongation mainly about y-axis. Sigma z will result in the elongation along the z-axis. But there is one more thing, that is the Poisson's effect. Poisson's effect is, let's say, first sigma x. When sigma x will act on the element, it will sigma x will produce the elongation or the strain along the x-axis. ठीक है जी? Now, when sigma y will act due to the Poisson's effect, ठीक है जी, it will also produce a strain in x direction. This stress sigma z will also produce a component of the strain in x direction. I repeat, sigma x when it will act, ठीक है जी, normal stress, it will produce a normal strain epsilon x, ठीक है जी, along the x-axis, and there will be lateral strains, ठीक है जी, mu times epsilon x, which will be produced along the z direction and along the y direction. ठीक है जी. Similarly, sigma y when it will act, ठीक है जी, when it will act on the face, it will produce a elongation strain along the y-axis, and a component of that strain will also be acting along the z and x-axis. Similarly, when you have normal stress about the z-axis, you will have a normal strain about the z-axis, and a component of that strain will also be produced in x and y. So basically, it means when I say in the x direction, there is a normal strain. There is normal strain due to sigma x, and then there is lateral strain due to sigma y and lateral strain due to sigma z along the x-axis. So it means along the x-axis there are three strains. Similarly, along the y-axis there is normal strain epsilon y, and then there is a component of the strain which is produced due to epsilon x, ठीक है जी, in y direction, and epsilon z in the y direction. So along the y there are again three strains. One due to the normal stress sigma y, and other due to the sigma x and sigma z. Similarly, in the z direction, you have sigma z, which will produce a normal strain epsilon z, and then there will be a component of the strain due to sigma x and a component of the strain in the z direction due to sigma y. ठीक है जी, so it means in each direction there will be three strains. One strain is your normal strain, and the two other strains are your lateral strains, which will be function of the Poisson's ratio. Now, different material have different Poisson's ratio. Like steel has the Poisson's ratio 0.3, concrete has 0.2. ठीक है जी? So it's dependent on the material properties. So strains are dependent on the material properties. Is this point clear?
Yes, sir.
Okay, if it is clear, then let's start with this generalized Hooke's law. So if the material at a point is subjected to a state of triaxial stress, sigma x, sigma y, and sigma z. So on the element, triaxial stresses are acting, sigma x, sigma y, and sigma z. So associated normal strains will be epsilon x, epsilon y, and epsilon z. So due to sigma x, epsilon x will be produced due to sigma y, epsilon y will be produced due to sigma z, epsilon z will be produced. ठीक है जी? So associated normal strains epsilon x, epsilon y, and epsilon z will be developed in the material. The stresses can be related to the strains. How they can be related? Using simple Hooke's law. Stress is directly proportional to the strain. Stress is equal to modulus of elasticity times the strain. The stresses can be related to these strains because see here, over here we made an assumption. We assume that the material is homogeneous and isotropic and behaves in linear elastic. So linear elastic means that the Hooke's law is applicable. The stresses can then be related to these strains by using the principle of superposition. Okay, superposition means that you superimpose the sum of three strains. Like along the x direction, if I talk along the x-axis, I have epsilon x due to sigma x, then I have lateral strain in x direction due to sigma y, then I have lateral strain in x direction due to sigma z. So associated normal strains will be developed in the material. The stresses can be related to these strains by using the principle of superposition. Poisson's ratio is lateral strain is equal to mu time longitudinal strain, and negative sign lateral strain will always be negative in what you say direction as compared to the longitudinal strain, because when you tested the steel bar in tension along the longitudinal axis there was elongation in the steel bar. However, along the diameter there was reduction because the lateral strain resulted in the contraction of the element, resulting in the reduction in the dia of the bar. ठीक है जी. And Hooke's law, as it applies to the uniaxial direction, so stress is equal to strain is equal to stress over modulus. ठीक है जी. For example, consider the normal strain of the element in the x direction caused by separate application of each normal stress. So now this is the combined deformation, or combined, you can say, strain elongations in the element. If we consider this one by one first, there is only sigma x acting along the x-axis. It has produced this strain. Now we have to find the magnitude of the strain acting along the x direction. First, we will compute the magnitude of the strain due to sigma x acting along the x direction, then the component of the strain acting along the x direction due to strain sigma y, then we have to find the component of the strain acting along the x direction due to sigma z. So when sigma, so consider the normal strain of the element in the x direction caused by separate application of each normal stress. So when sigma x is applied, figure 1018b that we have discussed now, the element elongates in the x direction and the strain produced is designated as epsilon x dash. So epsilon x dash is the strain in the x direction due to the normal stress sigma x. So epsilon strain x dash is equal to sigma x over E. Epsilon x dash is equal to sigma x over E. Now, due to the application of sigma y, which causes the element, now this stress sigma x produces the epsilon x dash, which was tensile stress, so correspondingly tensile strain, so there was elongation. Element elongates in the x direction, so your lateral strains produced by the stresses sigma y and sigma z, they will produce contraction opposite to the initial elongation. So application of sigma y causes the element to contract with a strain epsilon double dash x. So now epsilon double dash x will be sigma y over E. So this is your epsilon y. This is your epsilon y, sigma y over E times the Poisson ratio. ठीक है जी, and times the negative sign. ठीक है जी. So application of sigma y causes the element to contract with a strain epsilon double dash x. ठीक है जी. So epsilon double dash x is equal to epsilon y times the Poisson ratio times minus sign. Likewise, application of sigma z causes the element to contract with a strain epsilon x triple dash. So that will be epsilon z times the Poisson ratio times minus 1. Is this point clear? Is these three strains clear? If you have any question about these three strains, you can ask me now. Ji.
Sir, total strain in x direction will be summation of 3.
Yes, ये तो हाँ जी, ये अभी हम वो भी करने लगे. So when these three normal strains are superimposed. Let me show you here. I have solved them. So this is strain epsilon x dash due to sigma x. This is strain epsilon x n, जो in the book they are represented double dash, which is due to sigma y. Then this strain sigma z into sigma z over e minus mu sign. So now we will superimpose. So when these three normal strains are superimposed, the normal strains, the normal strain epsilon x dash is determined from the state of the stress. So what we will do, we will just simply add these strains. So epsilon x, the total strain in the x direction is sigma x over e. This is the strain due to normal stress sigma x. This minus mu times sigma e is the strain in the x direction, which is basically lateral strain in the x direction due to the normal stress sigma y. And this is the lateral strain in the x direction due to sigma z. Sigma x over e minus mu times sigma y over e minus mu times sigma z over e. So taking modulus as constant, so 1 over e will become sigma x minus times mu into sigma y plus sigma z. ठीक है जी? Is this point clear? So final strain or total strain epsilon x in the x direction is equal to 1 over e, that's the modulus, times sigma x minus mu sign times sigma y plus sigma z. If you see this, this is a modified form of a Hooke's law. Earlier you have the Hooke's law as sigma x is equal to sigma x over e. Epsilon x was equal to sigma x over e. Now when you will have multi-axial stresses, you can see it is very much similar. Sigma x minus this strains, ठीक है जी, minus these strains. This is the normal strain and these are the lateral strains which are acting in the transverse direction to the longitudinal direction. So this final expression epsilon x is equal to 1 over e times sigma x minus mu times sigma y plus sigma z. Is this clear?
Yes, sir.
Okay. Now on the similar basis, we can derive these two equations. I can explain to you and then you can do it yourself. ठीक है जी, epsilon y is equal to 1 over e sigma y normal stress minus mu times sigma x plus sigma z. ठीक है जी? So when I say epsilon y, the normal strain in that case will be sigma y. So it will produce the normal strain, whereas sigma x and sigma z, they will produce the lateral strains, which will be in opposite direction to the normal strain. Similarly, epsilon z, it is produced due to the normal stress in the z direction plus minus the strains in the lateral direction due to other normal stresses. So these equations represents the Hooke's law in a general form for a triaxial stress state. Now let's see if I want to compute normal, let's say compute the strains in y direction. So first there will be normal strain, ठीक है जी, there will be normal strain. Let's say I say this, so this will be epsilon dash y and that will be equal to sigma y over e. Then over here you can say application of sigma x causes the element to contract with a strain epsilon double dash y. Epsilon double dash y will be equal to minus mu times sigma x over e. Likewise, application of sigma z causes a contraction, that is epsilon y triple dash is equal to minus mu times sigma z over e. So in that way you will get the sum of the strains acting along the y direction. Then similarly you can do it for the Z direction. So in that case, the element elongates in the Z direction. ठीक है जी, when sigma Z is applied, so epsilon Z dash will be equal to sigma Z over E. And application of sigma Y causes the element to contract with a strain of epsilon double dash Z, which will be epsilon double dash Z will be equal to minus times mu into sigma Z over E. And the application of sigma Z causes a contraction such that epsilon Z triple dash will be equal to minus times mu into, ठीक है जी, बेसिकली यहाँ पे हमने x रह गया हमारा, तो दिस इज बेसिकली यहाँ पे x आएगा, z हमने ऊपर अज्यूम कर लिया था. So epsilon triple dash z will be equal to minus times mu times sigma x over e. So you will get the strains in z direction. ठीक है जी. So similar equations can simply be developed. I have explained you how to do it, so you can do it yourself. ठीक है जी, आपने सिर्फ अब उसको add up करना है. And the final results you will get as epsilon x is equal to 1 over e times sigma x minus mu times sigma y plus z. Epsilon y is equal to 1 over e times sigma y minus mu times sigma x plus sigma z. Similarly, epsilon z is equal to 1 over e, that is the modulus, times sigma z minus mu times sigma x plus sigma y. Just you can keep this thing in mind if you are calculating normal strain in the z direction. Normal stress is sigma z, other two stresses are lateral stresses. These three equations express the Hooke's law in a generalized form for a triaxial stress state. Guys, you must keep these equations in mind. Okay, and you should know how to derive these equations. Okay, so these three equations express Hooke's law in a general form for a triaxial state of the stress. For application, tensile stresses are considered positive quantities and compressive stresses are considered negative. So if a resulting normal strain is positive, it indicates the elongation, whereas a negative normal strain indicates the material is contracting. ठीक है जी, so this was all about the generalized form of the Hooke's law. Now comes this, this was about the new, what you say, normal stresses. Now about the shear stresses. Now, if we apply a shear stress, there are three shear stresses in triaxial stress state. Tau xy, tau xz, and tau yz. ठीक है जी? So now you have three shear stresses. So if we apply a shear stress tau xy to the element figure 1019A. ठीक है जी? So we have applied this shear stress tau xy. Then we have this figure B in which we have applied the shear stress tau yz. And then we have this third figure in which we have applied the shear stress tau zx. Now you see this, that actually what's happening here, that when you are applying the shear stress in one direction, there will only be a shear stress, correspondingly it will be producing the strain only in that direction. ठीक है जी? Tau xy, shear stress tau xy will only produce the shear strain gamma xy. There will be no shear strain in yz or zx direction. ठीक है? Similarly, yz shear stress tau yz will only produce the strain gamma yz. It will not produce gamma xy or gamma zx. Similarly, shear stress tau zx will only produce the shear strain gamma zx, and it will not produce the shear strains gamma xy and gamma yz. Reason is written here. If we apply a shear stress tau xy to the element experimental observations indicate that the material will deform only due to shear strain gamma xy. So you have shear stress tau xy, and the material will only deform due to the shear strain gamma xy. That is, tau xy will not cause other strains in the material like gamma yz or gamma xz. Likewise, tau yz and tau xz. Tau yz will only produce the shear strain gamma yz, and tau xz will only produce the shear strain gamma xz. ठीक है जी. So Hooke's law for the shear stress and the shear strain, ठीक है जी, Hooke's law for the shear stress and shear strain can be written as, ठीक है जी, if you recall in your material strength of materials, you have studied shear stress is equal to modulus of rigidity. ठीक है, shear stress is equal to modulus of rigidity times the shear strain. So G is the modulus of rigidity. Its value is around modulus of elasticity is 200 gigapascals. Modulus of rigidity value is around 76 gigapascals. So gamma xy is equal, shear strain in xy direction will be equal to tau xy over G. There will be no shear strain in other directions. So tau yz will produce the shear strain gamma yz only. So gamma yz is equal to shear stress tau yz over G. Gamma xz will be equal to tau xz over G. ठीक है guys, if you have any question, please ask me now. If no question, then we are proceeding further. So next is so this was generalized what you say Hooke's law for normal stresses and shear stresses. So this equation 1019 and the equation 1018, you should know how to derive them. Okay, I have explained the derivation of these two equations. Now next thing, relationship involving modulus of elasticity, modulus of rigidity, and the Poisson's ratio. So now you have to derive a relationship. So relationship is G is equal to E over 2 times 1 plus mu. So we have to derive this relationship. G is equal to E over 2 times 1 plus mu. ठीक है जी? This derivation we are going to do now. Are you guys ready for this?
Yes, sir.
Okay. Now we start with this element. ठीक है जी? On this element, so एक सेकेंड, आपको ना मैं यहां से हैंड रिटन इज मोर सिंपलर. So to derive this relationship, ठीक है जी, ये relationship है. So to derive this relationship, consider an element of the material is subjected to pure shear stress. ठीक है जी, this is your element subjected to pure shear stress tau xy. When element is subjected to pure shear stress, this means sigma x is equal to sigma y, which is equal to sigma z, and which are equal to 0, because we are saying that the element is subjected to pure shear stress, means tau xy, there is only shear stress tau xy, and the normal stress is sigma x, sigma y, and sigma z. They are 0. Agree with this? No. Now we have this equation to calculate the principal stresses. Sigma 1 comma sigma 2 will be equal to sigma x plus sigma y over 2 plus minus under root sigma x minus sigma y over 2 square plus tau xy square. ठीक है जी. Now when you have sigma x and sigma y both equal to 0, so when I will put the value of sigma x 0, sigma y 0, so this will be 0, sigma x sigma y 0, so this will be 0. So only element left in this equation is under root tau xy square, so that means it is plus minus tau xy. So your principal stresses, the maximum principal stress will be tau xy, whereas your minimum stress will be minus tau xy. Agree up to this point?
Yes, sir.
ठीक है जी. So when I put the values, I got the principal stresses, maximum normal stress, which is your major principal stress, sigma minimum is your minor principal stress. So we got tau xy and minus tau xy. Now this element must be oriented at an angle theta p is equal to 45 degrees counterclockwise from the x-axis. ठीक है जी. You can calculate the orientation of the principal planes from this data. You will get the answer theta p as 45 degrees. So now over here this element is shown which is oriented at an angle 45 degrees. So you can see this shear the stress. ठीक है जी. This is major principal stress, this is minor principal stress. Minor principal stress is negative, so that's why shown inverse compressive, and this is shown tensile. Sigma max is equal to tau xy, sigma minimum is equal to minus tau xy. Now if the three principal stresses, if you recall, in case because we were studying by axial stress state or the plane state of the stress. So in that case, we only had the major and the minor principal stresses. But in the book, at one point it was, we did study that the intermediate principal stress. Intermediate principal stress is basically, you can say, the average of the maximum and minimum. You can see average of maximum and minimum is 0. ठीक है जी. So maximum is tau xy, minimum is minus tau xy, so in between is 0. Okay, now you have sigma maximum tau xy, sigma minimum minus tau xy, which is basically sigma y. ठीक है जी. Along the y direction है जी. Along the y direction it is minus tau xy, along the x direction it is tau xy. So this sigma interior is basically your sigma z in your biaxial stress state or plane state of the stress. So sigma z is 0. Now this is the generalized Hooke's equation which we have derived earlier. Now we are going to put the values of this shear this maximum stress, minimum stress, intermediate stress in this equation. So you have this equation, epsilon x is equal to sigma x over e minus mu times sigma y over e minus mu times sigma z over e. Now the principal strain, so if you will put the values of the normal stresses that are principal stresses, ठीक है जी. These normal stresses are basically your principal stresses. Sigma maximum is major principal stress, this sigma y is your minor principal stress, this sigma intermediate is sigma z, which is 0. So when you will put the major and minor principal stresses in this equation in the form of sigma x and sigma y, you will get the principal strain. So the principal strain epsilon maximum can be related to the shear stress. How they are relating it? In this equation, sigma maximum is tau xy, which is along the x direction, ठीक है, x dash direction, which is oriented at 45 degrees. So we are replacing sigma x with tau xy. E remains the same, minus mu times sigma y over e. Sigma y is your minor principal stress, which is oriented along the y dash direction. So this value is minus tau xy. Sigma y is minus tau xy. Sigma z is 0. The principal strain epsilon maximum can be related to the shear stress. Now epsilon maximum, epsilon x will become epsilon maximum. sigma x become tau xy over E minus times mu. Sigma y will become minus tau xy over E minus mu times sigma z is 0, intermediate stress, so 0. So after simplification, epsilon max will become tau xy E minus this minus minus becomes plus, plus mu times tau xy over E. So I take tau xy and E as what you say common, and I take them out. So epsilon maximum becomes tau xy E over E into 1 plus mu, and this is my equation number A. If you have any question about this part, please ask me now. If this is clear, then I am proceeding further. Clear? Clear?
Yes, sir.
Okay. So this strain, epsilon max, the principal strain, which deforms the element along the x dash axis. This is the x dash axis along which you have the major principal stress. So this strain, which deforms the element along x dash axis, can also be related to the shear strain gamma xy. Can also be related to the shear strain gamma xy. So sigma x is equal to sigma y is equal to sigma z, and that is equal to 0, because at the start we have said that the element is subjected to the pure shear stress. So normal stresses are 0. So I can calculate epsilon x. I have the formula. Epsilon x is equal to 1 over E times sigma x minus mu times sigma y plus sigma z. Sigma x, sigma y, sigma z, they are all 0. So epsilon x becomes 0. Epsilon y is equal to 1 over E times sigma y minus mu times sigma x plus sigma z is equal to 0. Y, x, z, all these three normal stresses are 0. So normal strain sigma y will be 0. So you have these two normal strain values, ठीक है जी, coming out as 0. ठीक है जी. Now substituting just a moment. So substituting these values of epsilon x and epsilon y 0 in this equation to get the major and minor principal strains, epsilon 1, epsilon 2 is equal to epsilon x plus epsilon y over 2 plus minus under root epsilon x minus epsilon y over 2 square plus gamma xy over 2 square. Epsilon x, epsilon y, epsilon x, epsilon y, they are 0, 0. So under the square root, you will have gamma xy over 2 square. So final expression will become plus minus gamma xy over 2. ठीक है जी. So epsilon 1, the major principal strain. So epsilon maximum, that will be gamma xy over 2. That will be epsilon 1 will be equal to epsilon maximum, that is gamma xy over 2. If you have any query about this part, ask me now. यहाँ पे आपका epsilon maximum क्या था? Epsilon maximum from the equation A is what you say epsilon maximum यहाँ पे आपने पहले निकाला हुआ है तो xy over E times 1 plus mu, and over here we are now getting epsilon 1 is equal to epsilon maximum, that is equal to gamma xy over 2. Now according to the Hooke's law क्या है? Hooke's law, we said just in a short while ago about the shear strains, we said that the shear strain gamma xy will be equal to tau xy over g. ठीक है जी, यही हमने कहा था ना अभी in a short while ago. So epsilon maximum basically now becomes this tau xy over 2g. ठीक है जी, ये epsilon maximum becomes tau xy over 2g. ये this expression we are getting from here. ये short while ago हमने ये किया तो है gamma xy equal to 1 over g into tau xy. So gamma xy is equal to tau xy over g. So applying Hooke's law, gamma xy becomes equal to tau xy over g. So epsilon maximum is equal to tau xy over 2g. ठीक है जी, 2g. Is this part clear? If you have any query, please ask me now. No query? Okay. Then what you will do, you have epsilon maximum tau xy over 2g. What you can do, you have epsilon maximum is equal to tau xy e into 1 plus mu. Put epsilon maximum as tau xy over 2g. ठीक है जी? Equate two equations and you should simplify. If you can see, I have written it with a pencil here. Tau xy over 2g is equal to tau xy over e times 1 plus mu. After simplification, you will get this final expression. Now I can show you from the book as well. So what they are doing, first, very simple, one way to derive this relationship is to consider an element of the material subjected to pure shear stress. Okay, normal stress is at 0. Orientation of the principal planes is 45 degrees. Sigma max, you can put it in the equation, you will get sigma max maximum normal stress as tau xy, minimum normal stress is minus tau xy. This sigma max is major principal stress. This sigma minor is your minimum is minor principal stress. ठीक है जी? Then if the three principal stresses are acting, then you have major principal stress, which is tau xy. ठीक है? Intermediate is 0 and minimum is minus tau xy. And then we got this equation, if you see this, by substituting the values of sigma max, sigma minimum and sigma intermediate into the equation. Epsilon x is equal to sigma x over e minus mu times sigma y over e minus mu times sigma z over e. We got this. Then in the second part, sorry. Then in the second part, what we are doing, this strain which deforms, this is the maximum strain, so this is principal strain, deforms the element along the x dash axis can also be related to the shear strain gamma x y. So to do this, first note that sigma x, sigma y, sigma z 0. So then we have found that from the principal strain equation we get this. ये तो आपके पास Hooke's law से 0 आ गया. Then from the principal strain equation we got this epsilon 1 is equal to epsilon maximum is equal to gamma xy over 2. ठीक है जी? Then choosing the Hooke's law, gamma xy is equal to tau xy over g. So we then got epsilon max as tau xy 2g. ठीक है जी? Then we have put these two equations equal, this and this. ठीक है जी? I have done in my handwritten notes, I have done it in all the steps, so there should not be any issue. If you have any query, please ask me now.
Sir, this equation, can you please
थोड़ा
explain
सा
it?
ऊंचा बोलें, please.
Sir, equation number A. Can you explain it again, please?
A,
Yes, A.
यहाँ से
Sir, इससे नीचे.
ऊपर के नीचे.
नीचे सर. ये tau xy over e into 1 plus mu, this equation.
अच्छा, ये वाला. Sigma x was tau xy, so tau xy over e minus mu times sigma y was minus tau xy, minus tau xy over e. Sigma z was 0, so tau xy over e, this minus minus will become plus, plus mu times tau xy over e. ठीक है जी? Then we have taken tau xy over e common, तो यहाँ पे आ जाएगा 1 plus mu. tau xy over e I have taken common, so ये 1 आ जाएगा plus mu. Clear?
Okay, sir. Yes, there was an issue of sign. Thank you.
So sigma y was minus. आपकी क्लास है 10 बजे?
Yes, sir.
Over one equation is left. वो इतनी जल्दी हो नहीं सकती. ठीक है. Okay. ठीक है, guys. That's it for today. Now, in our strain transformation, two things are left. One, this dilation and bulk modulus equation is left. Okay? This equation is left, and other is theories of failure. Other thing we can do, I have class 11 to 12. So, unka bhi most probably I will finish up till this point. If you guys can come for 10-15 minutes at 12 o'clock, तो हम ये भी खत्म कर लेंगे. Possible है, then we do not need a separate class tomorrow. आप लोग अगर 12 बजे आ जाएंगे ना, I will send you a link. You can join the meeting at 12 o'clock. So we will take just 10 to 15 minutes and we can do this dilation and bulk modulus equation as well. ठीक है कि नहीं ठीक है?
Okay, sir.
ठीक है जवाब, मैं आपको जो लिंक होगा that I will send you by WhatsApp, क्योंकि उसमें जो होता है कि आप टीम्स पे 2 क्लासेस इकट्ठी एंटर नहीं कर सकते, तो वो डी सेक्शन वालों की चल रही होगी और आप लोगों को मैं एंटर कर लूंगा. ठीक है?
जी sir. Okay.
Thank you. Okay guys, thank you very much. See you later on. Just a moment, please do not leave. मैंने आपके अटेंडेंस डाउन. Just a moment, please.